Okay, welcome back. So yesterday we had kind of a marathon session of adding, subtracting, and multiplying fractions. And we had just begun talking about dividing. We watched the video, and I think we went through maybe two examples when I realized, maybe people wanted to get out and see the eclipse. So I hope some of you had a good chance to see it. So let's pick up where we left off. If you were absent yesterday, no worries. We're going to go through this step by step, so that should be good. Okay. Um, so, who is there anyone who can kind of summarize how when you have two fractions that have to be divided, how do you go about doing it? Who can kind of in a few seconds just tell us what the process is?
Aren't you supposed to flip one of them?
Yeah, you flip one of them. Good. So the thing to remember, let me write it down, is keep, change, flip. And let me change the color because right now I have white on white, which doesn't work. There we go. And I can make it bigger even. There we go. Okay. And someone just came in, Stacy. Okay. Yeah, thanks, G. Yeah, it's keep, change, flip. And let's actually take a look at what that means then. So the first fraction, again, it's hard to divide fractions. So what we want to do to calculate that is to change it into a multiplication problem. So you keep the first fraction the way it is, you change the division to multiplication, then you get the reciprocal. In other words, you flip the second fraction. So instead of dividing by 1/4, you can multiply by 4. 4/1 is the same as 4. So yeah, so that's the reciprocal um, when you flip the number upside down. Now, before we actually go and do this one, let's just use logic for a second. If I'm dividing 3/4 by 1/4, I'm asking how many times does 1/4 go into 3/4? What do you think the answer is?
3.
3, yeah. So sometimes it's pretty simple. So before you jump in, thanks, Teresa. Before you jump in and starting to flip and change and all that, sometimes the problems are really self-evident. You don't even need to do any of that. But let's go through the process. So we're changing 3/4 divided by 1/4 to 3/4 times 4/1. If I multiply across, I'll get 12, 3 times 4, over 4, 4 times 1. But remember that rather than doing that, we can try to simplify first. Now we have a 4 on the bottom and a 4 on the top. So what does that turn out to be?
1.
Yeah.
1.
Good. Any number divided by itself is 1. So if I have 4/4, that drops out. Any number where you have the numerator and the denominator the same, 4/4, 10/10, a million over a million, it's all 1. So now all we have left here in this problem in the numerator is 3 times 1. And in the denominator, 1 times 1. So that gives you 3/1, which is simply 3. And there's the answer, right? Which again, this was a kind of easy one that some of you may have seen right away. 3/4 divided by 1/4 is 3. For example, let's say I got change and I had 3 actual quarters laid out in front of me, and I wanted to know, I wanted to ask how many 1/4s go into those 3. The answer is 3. It's really simple, right? So any questions on this one? Okay, let's try the next one. So I was going to put you in breakout rooms and have you do this, but I thought, no, let's just work on it together. So I'm going to ask for volunteers. It'd be great, like if each of you could do one of them. Who would like to volunteer for the first one?
Well, excuse me, I can't see anything.
Okay, am I sharing my screen? 1 second. Yeah, I am sharing. You have to move some windows around. Is there anyone else who can't see it? Everyone can see what I'm doing on the screen?
Yeah,
So Ashara, are you working on a laptop or a phone?
laptop.
So maybe you have to just move some windows around so it's not hidden. It might be behind something. See if you can find it. Because otherwise it's going to be hard for you to follow along if you can't see it. Got it yet?
Yes.
You should see a screen that has some fractions on it, and the top says keep, change, flip, and the word reciprocal?
No, I don't see
Not
it.
yet?
I was having issues of hearing audio too.
Yeah, I see that. Okay, well, I don't, do you want to try to share your screen with us and see if I can problem solve for you?
Yeah.
Because I don't want you to be flying blind.
How do I share?
At the bottom of the Zoom window, there's a bar of commands, and one of them should say share with a green arrow that points up. If you click on that, then it will give you all your windows, and you pick which one you want to share. See if you can find that.
See, that's not doing that either. I
No?
think, yeah, something's wrong.
I don't know. Do you want to try to log out of Zoom and come back in?
Yeah, I'm gonna do that.
Okay, do that. I'm going to continue, but you won't miss too much, okay?
All right, I'm
Okay,
doing now.
okay, do that. Okay, so who's volunteering for this one? We each of you is going to get to try one, so don't be shy. Jose, I
I'll
see you
try
on.
it.
Okay,
Yeah, I got 11 and 22 go into each.
I mean, people all
sorry, Teresa. Yeah, I saw Jose unmuted himself, so I think he jumped in first. You can go next. Sorry about that. Go ahead, Jose.
Yeah, 11 is 1 and that's 2.
Okay, good. Yeah, 11 goes into 22 twice. What about 9 and 7? Anything you can do there?
No,
No. Okay, good. So what do you have in the numerator?
18.
Good. 9 times 2 is 18, and the denominator is 1 times 7. So you have 18 sevens. Can you change that to a mixed number for us?
Yes, sir. 7 goes into 18 twice.
Good.
leaving-
7, 14, 21. It only goes in twice. Good.
And then you got 4 left over, so that would be your numerator.
Good.
And then you leave the 7.
Excellent. Thanks, Jose. Any questions for Jose on that one? Got it. Okay, Teresa, thanks for being patient. Do you want to try this one?
yeah.
Okay.
Keep the 1/2,
Okay, good.
flip the 3/4,
Okay.
multiply.
Okay.
That's
Can you,
4 over
before
3.
you multiply, can you simplify
Yes.
anything?
Yes, I can simplify the 1 and the 4.
Well,
So the 2, I
we-
mean the 2 and
2
the
and the 4.
4.
Okay,
Sorry.
good. No, that's
Sorry.
fine. Mhm.
The 2 becomes a 1 and the 4 becomes a 2.
Excellent. So then what do we have?
And we have 2/3.
Good. So you have 1 times 2 over 1 times 3.
Times
And it's
3.
simply 2/3. Great. So if I ask how many 3/4 go into 1/2, that's hard to visualize, hard to imagine. But if you change it to a multiplication problem, then it's a lot easier. Thanks. It becomes 2/3.
Okay.
Great. Okay. Who would like to try number 6?
I'll try.
Let me mute myself.
You know what? One second. You need to let. Oh, can everyone see that at the bottom of the screen here? Or
Number
is it cut,
6?
is it cut off? Can you see that?
Yeah, I can see number
Okay,
6.
so okay, Sheena, why don't you do this one? Then I'll grab the screen as a screenshot for. Okay, so what are we gonna do?
All right, I got 7/8, and then I flipped the 1/4 to make it 4 over 1.
Okay, good.
The 4 goes into 4 one time.
4 goes into 8. How many times?
I mean 2.
2. Good. So 4 goes into 8 2 times, and then what are you left with?
I'm left with 7 times. Oh,
Yeah, 7 times 1.
I changed that 4 to 1. 7 times 1 is 8, and so it's 8 over 2.
It's 7 times 1, not 7 plus 1.
No, that's what I said. 7 times. You didn't hear me? Oh,
Yeah, but
shoot,
7
my
times 1
bad.
is
Okay,
7.
no. You're right.
Okay, that's fine. So
You're right.
it's 7
2 over
halves.
7. Yes.
Good. 7
So
over
2 goes
2.
into 7 3 times.
Okay.
You have 1 left over, so it's
2,
3
4,
and 1/2.
6. Good. 3 times plus 1 left over. So 7 halves is the same as 3.5. Excellent. Great. Okay, let me grab this screen. Yeah, there we go. And 1 second, I have to stop. I forgot I have to stop my tools first. And then click on the share button. It's not letting me do it. 1 second. Sorry. Yeah, now it works. Okay. Okay, great. So let me grab this. I'll put it in the email. that I am going to send you today. There we go. Okay, good. Okay, so we don't need to do, where am I? This page? Yeah, let me just clear. We don't need to do lots and lots, but let's see who else would like to give it a shot and try. Ashara, can you see the screen yet? This time?
No,
Still
no.
can't. I'm sorry. Yeah,
Yeah.
I don't know what's going on.
I did exit out by accident.
Okay.
So I don't know if that affected it.
Okay, so the only thing I can say is that when I send the email, you'll see the screenshot and also you
Okay.
can watch the video, but yeah, I don't know how to problem solve it right now.
I don't-
So does anyone want to jump in and try 7, 8, or 9?
I'll try 7.
Okay, Shanita, you just did one, right?
Yeah.
Okay, so that's great. I'm glad you're champing at the bit to do more, but let's just see if
Okay.
anyone else wants to try it. Because especially, and I'm going to ask the students who are not completely confident, you're the ones really who should try it, because I'll lead you through it and then you'll feel more confident on how to do this. Anyone want to try one?
Mr. T, I have just a quick question.
Okay, so G, you're
Um,
volunteering. Ask the question and then you'll do one of these.
When the problem that was 7/8 divided by 1/4.
Yeah.
The answer was 7/2, and then into like a mixed number that was 3/3.5, right?
You're right, it was 7 halves. And then you ask how many times does 2 go into 7? 2, 4, 6. It goes 3
Right.
times, and then you have 1 left over, so that becomes 3.5.
All right, bet.
Okay, good. Yeah.
And you
Okay,
said you
so
wanted me to do number 7?
yeah, so let me scroll up a bit. Okay, yeah.
Okay.
So 7, 8, or 9, whichever one you want to do.
7's still like a lucky number. So
Oh,
I'll
good.
try that
Okay.
one, right? So 5 eighths, and I'm just writing this down. Divided by 15/6.
16.
15/16, thank you.
Yeah.
And then we flip it over.
Okay.
So we have 5/8 times 16/15.
Okay, good. Any simplifying you can do?
Personally, not gonna touch that because I'm only used to like same numbers.
Okay. Well,
No?
how about the 5 and the 15? Does 5 go into 15 a whole number of times?
I mean, I see it now, but it just looks so dangerous to touch it, you know?
Okay. What about, yeah,
Compared to like two of the same number,
right.
you know?
I get it. Right. Same number is easy. But what about 5 and 15? How many
I
times
mean,
does 5 go into
5
15?
goes into 5 one time and 5 goes into 15 3 times.
3 times, right? 5, 10, 15. So that
Right.
means that's a 1 and that's a 3. And then what about 8 and 16?
I mean, 8 goes into itself one time and to 16 2 times.
2. Good. So then that becomes a 2 and a 1, right? So what you're
Okay.
left with then in the numerator is 1 times 2, right?
Okay.
And the denominator?
It's 3, right?
1 times 3, right? So the answer is 2/3. Great. Okay, you got it.
Wow.
Okay.
Wow.
Okay, you got it. Great. So anyone else want to try one before we move on? There's 2 more if you want to try.
I'm
Sean,
just taking notes.
Angel, Nick, Stacy, Elizabeth, if you'd like to try one. Ashara, Ashara, I can read it aloud to you if you can't see it.
I'll do one.
Oh.
5/16 divided by 5/8.
Okay, 15 16ths. Yeah, that's 15 16ths, not 5.
You're right.
Okay,
Sorry.
Okay,
15 16
go ahead.
times. You flip that, which will be 8/5.
8/5, great. And then any canceling you can do before we multiply?
Yes. Same as before. The previous one. 5 goes into 5 once. The 15 turns into 3. The 16 turns into 2. The 8 turns into a 1. And then you have as the answer 3/2.
Okay, notice that, look at these 2 problems. Notice that they're flipped. 5/8 divided by 15 16ths and 15 16ths divided by 5/8. Now look at the answers, and the answers are flipped. This is 2/3 and this is 3/2. So pretty cool, right? Now,
So wait.
yeah, go
Oh,
ahead.
that's what I was about to ask. Don't we still simplify to make it a mix?
Yeah. So what's the next
Okay.
step to simplify?
Divided 2 into 3. which goes in one time, so it leaves you with 1 1/2.
1 and 1/2. Great. Okay, good. Yeah. Okay. And again, you might leave it as an improper fraction. It's going to depend what you're using it for. Okay, thanks, Stacy. I won't call on you. You know what you want to use it for, and also, you know, if it's a multiple choice test, if you don't see 3/2 as an answer, if the answers are in mixed numbers, then you know you have to change that to a mixed number. Okay, anyone else want to try one before we move on? There's one more left if you want. Okay.
That one I wanted to ask about.
Yes.
Okay, I did it. I did the problem. Do you want me to go over it?
Which one? Number 9?
Number 9, yeah.
Okay. Yeah, you want to lead us through it?
All right, so you got 7 over 12. You take the 3/4, so you flip it, you got 4 over 3.
Okay.
4 goes into 4 one time, 4 goes into 12 3 times. So now this was the issue. Do I change the denominator? And no, do I change the denominator or leave it because it's the same?
Okay, now, so what
Because
we're
I have
doing,
7/9
Right.
and
no, let's stop. Yeah, stop for a second. Now, remember that you're only concerned about common denominators when you're adding and subtracting fractions.
Mhm.
You now have a multiplication problem. We don't have to worry about common denominators. All you have to do is multiply across the numerators and multiply across the denominators. That's how multiplication works. So you have 7 times 1 is,
7,
and 3 times 3,
9.
9. Okay, and can you simplify 7/9?
No.
No. Okay, there's no common number that divides into 7 and 9. There's your final answer, and it's a proper fraction. So Shanita, you're good to go with that one.
Okay.
Right. And in fact, 7 is a prime number, so it only has itself and 1 as factors. 9 is 3 times 3, but 7 is simply just 7. Right. Some numbers don't have any other factors. 2, 3, 5, 7, 11, 13. 17, 19, 23, you know, there's a bunch of numbers like that. There's an infinite number of numbers actually that are called primes, and they're only divisible by themselves and 1. 7 is one of those. Great. Any questions on this before we move on?
Can you explain the arrows?
The 2 orange arrows?
Right.
Yeah. So I'm just saying that's multiplying across. When we multiply fractions, you simply multiply across the numerators and multiply across the denominators. So it's 7 times 1 and 3 times 3. Right.
So you multiplied 7 by 4?
Now the 4 we canceled out. The 4 became a 1. And the 12 canceled out. The 12 became a 3.
Oh, you did cancellation.
Right.
And then you just went ahead.
Right.
Okay. All right.
Now, if
Thank
we
you.
hadn't canceled, right, if you had just done the multiplication, you would have had 7 times 4 is 28, and 12 times 3 is 36. And then you would have had to figure out, how do I simplify that? What's a common number that divides into both? And you could see, well, I can divide them both by 4. 28 divided by 4 is 7. 36 divided by 4 is 9. So you still would have gotten the same answer. It's just you would have had bigger numbers. So again, I'm a proponent of simplifying first so that you don't have big numbers to work with. Good question. Thanks for asking that. Okay, let me grab this one and put it in your. Sorry, I have to. Okay, I'll put it in your email.
Mr. T, I got a question.
Yeah. Give me 1 second. I'll come back to that screen. Okay, there we are. Yeah, go ahead, Jose.
Yeah, sometimes the terminology will kind of confuse me. Like, you know, least common factor, greatest common factor, and then you have least common multiple, greatest common multiple. What is the difference?
Right. Yeah. A good question. And we're going to have a unit on both factors and multiples. So we will get to that. Factors are the numbers that, when multiply, create a bigger number, right? So, for example, glad you asked. So let's just look at it for a minute. So, for example, the factors of if I wanted to factor 15, I'm interested in what are the prime factors of 15. So 15 is 3 times 5. 3 and 5 are primes because they only have themselves and 1 as factors. So those would be factors. let's say I have 12. 12 is 2 times 6, but 6 is 2 times 3. So 12 is actually 2 times 2 times 3. So that's what's called prime factorization.
Okay.
So the
Okay.
did I spell it right? Factorization. Okay, here we go. So the factors would be 3 and 5, for example. The multiple is 15, right? So the factors are the small numbers that multiply together. And then the multiple is the larger number that they make once you multiply them together. Now, the multiples are what do you get when you multiply the factors, and the primes are the prime factors of the small numbers that multiply together. Some numbers are prime, they only have themselves and 1 as factors. So for again, 2, 3, 5, 7, 11, 13, etc. You can't factor those numbers because they only have themselves as a factor. Other numbers may have a couple of factors like 15. Other numbers like 60 might have many factors, lots of different ways to make 60. 2 times 30, 3 times 20, 4 times 15, 5 times 12. And it's like 60 is a number with multiple factors, which is why the Mayans used it in their calendars, because it's an easy way to split things up into different parts, because 60 has lots and lots of factors.
Could you say that
Oh.
again? That's why the Mayans use that in their calendar.
Right. So we have, in our Western civilization, we have a calendar kind of based on the months. Each month, I'm sorry, based on the moon. Each month is approximately a lunar cycle. Lunar cycle is really 29 and a half days. But so our calendar is kind of month based because, back when people were keeping track of time, they would be able to watch the moon go through its phases. Each time it went around all its phases once would be called a month after the word moon, right? So ours is kind of based on that. The Mayans had a sequence of 60 instead of our 30, like more or less. So their calendar was you could split it up into many different ways, because 60 is a number that has lots of factors. When we have a circle, we count a full circle as 360 degrees all the way around. Now, that's not anything magical or natural. People decided, we're going to say that a circle has 360 degrees. Why did they pick 360? Again, you can divide it many ways. 4 times 90, 2 times 180, 3 times 120. There's a lot of ways to split up 360. So the 360 for a full circle, the people decided a long time ago that that's what they were going to do, because it's an easy number to split in many ways, right? Okay.
60 minutes.
60 minutes in an hour, exactly, right.
But it's
So,
also
yeah,
a TV show.
Yeah, right. So we don't have 100 minutes in an hour, we have 60. But again, we can therefore have quarter hours, which are 15, half hours, which are 30. There's a lot of ways to split up 60. Okay, good. Let me grab this little thing at the bottom that kind of G led us through, which is good. So I'll put that in too. Okay, put it in now.
So basically, the factors is how you get to the number, and the multiples is the answer.
Yeah, good.
Whatever's
That's a good way of that's a good way of looking at it. Right? And again, we'll have a whole unit on factors and multiples coming up soon. That should make things even clearer.
Okay, thank you, Mr. T. Appreciate
Okay,
it.
good. Okay. Okay, so let's okay, so so the next thing is we've talked a little bit about improper fractions and mixed numbers and how you can convert back and forth from one to the other. So let's watch a video on mixed numbers. She's also going to talk about, again, proper and improper fractions, but it's it's not bad to get a review. And I think it's a different teacher this time, so you'll get a different person leading us through it. Okay.
Hi, and welcome to this review of fractions and mixed numbers. Before we dive in, let's review the basic parts of a fraction. Remember, a fraction simply represents a part of a whole. It has a numerator and a denominator, which tells us what the part is and what the whole is. Let's look at the fraction 3/4 as an example. We can see that the 3 is our numerator and the 4 is our denominator. So the fraction 3/4 is really saying 3 parts out of 4 parts total. It can also be helpful to visualize 3/4 as simply 1/4 plus 1/4 plus 1/4. It is very important to remember that a denominator of 4 does not represent the value of 4. A denominator of 4 represents the value of 1 that is divided up into 4 equal parts, or fourths. The type of fraction we're working with here represents a value less than 1 whole. 3/4 is not quite 1. If we had 4/4, that would be equivalent to 1. But we only have 3 out of 4 parts. We see and use fractions that are less than 1 all the time in our daily lives, whether it's for things like recipes or keeping track of time. Recipes often call for amounts such as 1/2 teaspoon of salt, and we often keep track of time in terms of quarter hours, like 3:15 for 3:15. Though we observe this type of fraction very frequently in our daily lives, it is not the only type of fraction. Consider the following scenario. You're ordering pizza for a big celebration. There will be lots of hungry guests at this celebration, so you order 3 pizzas. Each pizza is cut into 6 slices. This means that each pizza has 6 equal parts, and as a fraction, 6 would be considered our whole, or our denominator. If your first guest eats 2 slices, we would represent this as the fraction 2/6. 2 parts out of 6 parts total. But what if that first guest was really hungry and grabbed 7 slices? Again, each pizza was cut into 6 equal slices, so 6 remains as our whole, or denominator. But this time our part is 7. In this scenario, our numerator is larger than our denominator, 7/6. Fractions with a numerator larger than their denominator are referred to as improper fractions.
Okay, so
Which tells us what the part is
sorry.
and what the whole
There we go.
guests at this celebration, so you order 3
One
pizzas.
sec.
Each pizza is cut into 6 as improper.
Okay, sorry. Yeah, so in this example, more than 1 whole pizza was eaten. 1 whole pizza was eaten, which is 6 slices out of 6, and then another slice, a 7th slice from the second pizza was eaten. So in total, that person ate 7 out of 6, right? 1 whole pizza, which was 6/6, which equals 1, plus an additional 1/6 slice from the second pizza. So if you add those together, the 1 whole plus the 1/6 is going to give you a mixed number of 1 and 1/6. So 7/6 that is the same as 1 and 1/6. Again, they're exactly the same quantity. 1 is an improper fraction, 1 is a mixed number, but they're showing you the same quantity. Questions before I let her continue? Okay.
Proper fractions. Essentially, improper fractions equal a value that is more than 1. 1 whole pizza would be represented by 6/6, or 6/6. 7/6 represents 7/6, which is more than 1 pizza. This could be visualized as 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 plus 1/6 equals 7/6. It can also be written in another form called a mixed number. An improper fraction and a mixed number will represent the same amount, but simply be written in a different form. For example, the improper fraction 7/6 could also be written as the mixed number 1 and 1/6. Mixed numbers and improper fractions share the same amount, but as a mixed number, the parts are collected and consolidated into as many groups of 1 whole as possible. For example, 4/4 would be grouped together as 1. 7/7 would also be grouped together as 1. Any value where the numerator is equivalent to the denominator would be expressed simply as 1. In our pizza example, the guest took 7 slices from a group of pizzas that were sliced into 6ths. We said this could be represented as the improper fraction 7/6, or visualized as 1 over 6 plus 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 1 over 6. As a mixed number, we would group 6 of these sixths in order to form 6 over 6, or 1 whole. By grouping 6 over 6 together, we can see that 1 over 6 is left over. We would write our mixed number as 1 and 1/6.
Okay, so just to jump in and just put maybe a circle around it, just to make it really clear. We have this first pizza, the entire pizza was eaten, all 6 slices. So that gives us the 1 whole, right? The 6 sixths gives us 1. The second pizza, in which only 1 slice was eaten, then gives us that extra 6th slice. So that gives you 1 and 1/6. Or if you want to use it, if you want to just count it as 6, 7 sixths. Questions? Okay, let's continue.
Let's try a few more examples. Let's write the following improper fractions as mixed numbers. 4/3 can be visualized as 1 over 3 plus 1 over 3 plus 1 over 3 plus 1 over 3. We know that 3 over 3 is equal to 1, so let's group 3 of these thirds together. We are now left with 1 and 1/3 as our mixed number. 3 halves can be visualized as 1/2 plus 1/2 plus 1/2. We then know that 2 halves, 2 over 2, makes 1 whole, and we're left with 1/2 left over. So 3 halves as a mixed number is 1 and 1/2. Let's try one more example. 7/4. 7/4 is the same as 1/4 plus 1/4 plus 1/4 plus 1/4 plus 1/4 plus 1/4 plus 1/4. Now we know that 4/4 are grouped as 1 whole. So these 4/4 pulled over to equal 1, and we're left with 1, 2, 3/4. 7/4 written as a mixed number is 1 and 3/4. This process will take place in reverse in order to convert between a mixed number to an improper fraction. For example, if we started with a mixed number 1 and 3/4 and we wanted to convert it to an equivalent improper fraction, we would take a look at the whole number. In this case, it is 1. This whole number is really representing the denominator that's in the fraction. In this case, it's 4, so the 1 is equal to 4 over 4. When we combine these 4/4 with the 3/4, we end up with 7/4 total, or 7 over 4. That's all there is to it. I hope this.
Okay, so let me just go back for a second. That's too much of a close-up. There we go. Oh, got a funny face. That's better. Okay, so what she didn't do was show us the work this time. And let me just show you that, because right now what she's done this time is convert the other way. She said, how do you convert 1? Let me make that.
So she was saying, she was trying to explain what converting the answer from 7/4 back into 7/4.
Right. So she said, well,
Okay.
let's see how you convert it the other way. So let's say you have 1 and 3/4. What is that as an improper fraction? So the 1 here, like how many fourths is that? That's equivalent to 4/4,
4.
right? Plus, don't forget you had 3 to begin with.
Yeah, you got to add the 3.
Right.
So
another way of looking at it then is what you can do is you multiply the denominator times whatever whole number it is. And it's not always going to be 1. You might have 5 3/4, for example. And then you add back in whatever's on the top. So 4 times 1 is 4, plus 3 gives you 7, and you keep the denominator. So 1 3/4 becomes 7/4. Let's just do one more. Let's say I had 4 and 3/5. What is that as an improper fraction? So I want to change the 4 into fifths. You want to walk us through it, Shanita?
You times the 5 by 4, which gives you 20.
Okay, so that's 20/5 right there. Good.
And then you add the 3.
Plus the 3/5 you started with.
Yes. And then that's going to be 23 over 5.
Excellent, great. Anyone have questions for Shanita or me about, how she just did that? Good, we're all good. So you can convert back and forth, depending on, again, how you want to show the number. Okay. Let's see, I think she's finished. Let me let her finish. Right. Okay, so what I'm going to do now is give you a short quiz on fractions. If you're new, Shanita and Ted, and you haven't done one of these yet, I'm going to put the link in the chat. When you click on the link, it'll open up into Socrative. Let me show you what that looks like. I'll share that screen. There we go. And what you'll see, it says, this room requires a student ID. Please enter your student ID. Your student ID is simply your first name. All right. So
Okay.
enter your first name, and then click submit. That should open up the quiz.
Following is an improper fraction.
Sorry, and then there's 5 questions. So just answer the 5, and then we'll go over it together. Okay. If you're having any troubles logging in, let me know. I did mess up some student names the first time around. Hopefully I got it right now for everybody. Okay. And let me pause the recording while you do those 5 questions. Okay, everyone, you should see the quiz that says overview of fractions. Ashara, can you see it?
No.
Okay, again, see if you can manipulate Windows. Sorry about that. But
It's okay.
it'll be in the recording, and you'll get it. You have it in your email too. Okay.
All right, thank you.
Okay. Okay. So which of the following is an improper fraction? So 9 if you took it, and 9 if you got it right, which is great. So just tell us, someone quickly, how can you spot an improper fraction?
One number is bigger than the other.
Say it again, Jessica. Sorry.
The denominator is bigger than the numerator.
Are you
right?
sure? Say it again. You sure?
Opposite. You say the words.
I'm not saying. Somebody help me! Somebody help me!
No, so you
Janita,
right,
help
right,
me.
but it's the denominator is smaller than the denominator.
Right.
Yeah. Okay. Wait.
Yeah.
Okay. Let's just get it straight. The numerator is larger than the denominator. The top is bigger than the bottom, meaning it's more than 1. Or if they're equal to each other, that's still improper, right? So if you have something like 4/4, which equals 1, that's an improper fraction, because a proper fraction has to be less than 1. Or if you have greater than, so 5/4 is also an improper fraction, which is like 1 1/4. So those would be 2 examples of improper fractions, either equal to 1 or greater than 1. You could still work with it mathematically, but it's an improper fraction. How about we take 21/8 and convert it to a mixed number? Anyone want to try that?
8, 16, 2.
Good.
16, 17, 18, 19, 20, 21. 5/8.
Excellent. Yeah. So 8 goes into 16 twice. 8, 16, 24. It doesn't go 3 times. 8, 16, and then you have 5 left over. So that would be 2 5/8. Great. Okay, good. Okay, good. So fantastic. Everyone who tried it got that one right. Okay, so let's go on to number 2. Of Denisha's 8 clients, 6 have Apple MacBook Pros, and which of the following fractions is equivalent to these 6 out of 8? So we have 6 out of 8 right? What we want is an equivalent fraction, meaning a fraction that's equal to this. So what we want to do is reduce or simplify this. What can we divide top and bottom by?
2, right?
Yeah,
Two.
they're both even numbers. Now, 6 is divisible by 3 also, but 3 doesn't go into 8. 8's divisible by 4, but 4 doesn't go into 6. So that's as much simplifying as we can do, and then you end up with 3/4. Right. So the answer is A, 3/4. Okay, so 6 out of 8 is, if I said 6 out of 8 of your clients have Apple MacBooks, you would say it's 3/4 of my clients, 3/4 of my clients. Any questions on that?
Nope.
Okay, good. What percent would that be if it's 3/4? Anyone want to do that?
25.
25.
3/4, not 1/4. 3/4.
75.
75, right. 25, 25, 25. So that's 75%. Great. Okay, number 3, everyone got it right. Luis has a dozen clients. Of these, 2 have 13-inch and 7 have 16-inch Apple. Which fraction of his clients have MacBook Pro? So we're not interested in, what size they are. We just want to know how many. So it's 2 and 7 make 9 together. And he has a dozen clients. You have to know that a dozen is 12. And then what can I divide these by to simplify?
3.
3, yeah, 3 is a common factor. 3 goes into 9 3 times, 3, 6, 9. 3 goes into 12 4 times, 3, 6, 9, 12. So again, it just happens coincidentally that it's the same answer, 3/4 or 3/4. Questions?
No.
Okay, great. Yeah, again, everyone got it right. Good. Okay, good. Number 4, Fais's client, Park Slope Pediatrics. So this one was a little more challenging for some of you. Let's see why. 1/6 of their laptops have memory upgraded with 2 GB DRAM chips and 2/3 with 16 GB. What fraction have not been upgraded? So what do we have to find? We really have to find first how many have been upgraded, right? So if we have, no, we don't know how many, we just know fractions. But we have 1/6 that have gotten 2 GB upgrades, and 2/3 have gotten 16 GB upgrades. So how many is that altogether? Now we're adding fractions. What do I have to do to the fractions? What?
You gotta get a common multiple.
A common denominator.
Denominator?
Right. Common denominator. I can't change the 6 to a 3, so I'm going to change the 3 to a 6, right? So what you do is you multiply by 2/2. So the 1/6 is going to stay the same. The 2/3 becomes 4/6.
4/6.
I can add them together and get 5/6. So 5/6 have been upgraded. How many have not been upgraded? So what's left over is the 6/6 is everything. It's 100% minus the 5/6 that have been upgraded gives me a remainder of 1/6 have not been upgraded, right? So there was a lot you had to do with just this one simple problem. The first thing is you had to realize first that you had to add them together. Second, that because they were they were not common denominators, you had to get a common denominator. Third, then you had to subtract the 5/6 from the whole, from 6/6. So even one little problem
that's
can
what
have,
I did wrong.
right, can have multiple steps, right? Okay. Any questions on this one?
Yeah. All right. From the 5/6, because I just I forgot about the 1/6, and after I simplified the 2/3 to 4/6, I just put that down to 1/3.
Okay, yeah, but you got it now, right?
Yeah, I got it now.
Okay, good. Anyone else want me to do it again or explain it again?
Because it says not. That's the reason why we put
No.
the 6/6.
Yeah, because 5/6 have been upgraded. The question is, what's the remainder that haven't been? So it's 100% of something is 6 out of 6, right? So that would be if all of them have been upgraded. So 6 out of 6 is all of the clients. 5 out of 6 have been upgraded. 6/6 minus 5/6 gives you the 1/6 that have not yet been upgraded. Anyone do it a different way? Okay. Okay, good. Okay, and again, you'll get this in your email, so you'll have that explanation if you want to look at it again. And Teresa, I'll email you this whole file.
That problem took me so long to solve that when I got to the next one, I said you finished the test.
Yeah, sorry, but I did. Yeah, but now just pay attention along with us. Now, this problem is simpler than it looks. Sometimes math problems can be deceiving, and you think you have to go through a lot of manipulations. And many of you were trying to get common denominators and do all that. It's a lot simpler than that. Your client requires optical drives to be added to their MedCard computers. They report that 3 out of 7 on the main floor need upgrading, and 2 out of 5 on the second floor need upgrading. So first ask yourself, how many need upgrading altogether? Well, it's 3 on the main floor and 2 on the second floor. That's 3 plus 2. So what we know is that 5 altogether are going to need upgrading. Now, how many clients are there altogether? Well, there's 7 on the main floor and 5 on the second floor. So altogether, there's 12 clients, and there's your answer. So you didn't really have to try to get, so this wasn't a problem of trying to add 3/7 and 2/5 together. It was a lot simpler than that. And again, I put this in
I
here.
didn't do that.
Yeah, I put this in there just to show you that sometimes just stop for a minute. Don't go right to thinking it's as complicated as it might be. This was actually a really simple problem. Again,
yeah, I ended up with 6/35. I don't know how.
Yeah, again, it's not
bad.
Yeah, it's not to trick you. It's just to get you used to, thinking first. Think before you leap, right? Okay.
So we didn't have to simplify it because I changed everything to, making it. I made it the fraction 3/7 the way that they put it. That's the reason why. And 2/5. So I, did the same common denominator where I got 15 over 35, then plus 14 over 35, which gives you number 1.
Right. Which is the wrong answer. But again, that's why the answer's there, Shanita, because when test makers make up these tests, they ask themselves, well, what are the common mistakes students might make? Let me put those in the answers to see if they're choosing those answers. So that gives me a lot of information, right? So right away, I know that not only you, but 5 students altogether thought that they had to find a common denominator to add the 2 fractions. So that tells me a lot. So that's important to me as your teacher, which is why I'm explaining that, this is a lot simpler than it seemed. Okay. Any questions on this one? Do you hate me?
No, but
no, but okay, there's a but. Oh no.
No, because it's like, all right, these questions, the way they worded, that's the reason why, of course, we would do it the other way.
Right.
So where is the how would, like, because you came up with 12 instantly. So we were supposed to do the whole numbers.
Well,
not
she's asking for keywords. What keywords can she use?
It says the report says 3 out of 7, and then it shows you 3/7. Right. And then it says 2 out of 5, 2/5.
Right.
So we were just supposed to just add it straight across the way you did.
Yeah.
Okay.
And again, it was tricky. It was a tricky problem. I'll grant you that, but I put it in there specifically to just show you that sometimes just step back from the problem and think about actually what am I trying to find, and maybe this one was simpler than it looked. Okay, good. Which list of fractions are contain amounts that are all more than 1 whole, right? So if we look at A, 5/3, yes, it's an improper, it's greater than 1. 7/5, yes, it's an improper fraction, it's greater than 1. But 2/2 is not greater than 1. 2/2 equals 1. So that's not one of the choices because we want more than a whole. Let's look at B. 3/5 is less than 1. Nope. 7/5 is greater than 1. 3/2 is greater than 1. But the problem with B is A is not more than a whole. Let's look at D. 5/5 is equal to 1. 7/7 is equal to 1. And 3/3 is equal to 1. These are all equal to 1 whole, not more than 1 whole. So the only answer in which all 3 are greater than 1 is 5/3, 7/5, and 3/2. Okay. So it was asking for greater than 1, not greater than or equal to 1, right? If it had said which contain amounts that are greater than or equal to 1, then A and D would have been good choices, but not if it's all more than 1 whole. Who has questions on this one? You get it now? Okay. Again, the important thing is you get it now. Okay, number 7. Okay, you find you can lay down 2 1/3 feet of Cat5 cable per minute. Express this mixed number as an improper fraction. So we have 2 1/3. Let's remember how we do this. We take the denominator and multiply it by the whole number part. We're going to multiply that. And that gives us then 6/3, right? So 2 is the same as 6/3. But don't forget, we have to add that 1/3 back in. So the 6/3, which is 2, plus the 1/3 that we were given, gives you 7/3. Okay, any questions on this? No, if you answered A or D, think about it carefully. Make sure
Mr.
you
T, that was
get
the
it
whole
now.
question.
Say it again, G.
That was the whole question, to just change it from a mixed number to an improper fraction.
Yeah, express this mixed number as an improper fraction. That's the direction. Yeah, that's all.
So that's all that wanted you to do. Like
Yeah.
express 2 1/3 as an improper fraction.
That's it. That's all you had to do.
My mind went some other direction.
Okay. So, yeah. So,
I
one
thought
of
it
the things.
wanted us to express that first sentence
Yeah.
as
So what?
something.
Yeah. So one of the things, when you're dealing with word problems is to try to make sense of them. What exactly? 1 second. Okay, Teresa's having problems here. Yeah. So what exactly am I being asked to find? So, before you jump in and try to solve it, what exactly am I being asked to do? And it said express it as an improper fraction. So, read carefully. Okay. Now, this one, it's the opposite now. We're taking an improper fraction and we're trying to change it to a mixed number. So you ask yourselves, how many times does 3 go into 5? 3, 6 doesn't go in twice. It only goes in once. That gives us, so that would be 3/3, right? So that would be the 3/3. And then we have 2/3 left over. So it's 1 2/3. The 1 is equal to 3/3.
Yeah, I see where I made my mistake now.
Okay, so we have 2 more thirds left over. Okay. Questions on this one? Okay. Okay, let's look at number 9. Mr. T, this is another challenging one I gave you, so again, don't hate me. Mr. T orders sub sandwiches for his bridge class. He orders 8 subs and requests that they're each cut in 2/3. By the way, when I was teaching in the classroom, sometimes we'd order in food. We'd also have days when all the students brought in food. I missed that. So I'm hoping that maybe one day we'll have that again. But for right now, just use your imagination for the food, okay? Each sub is cut into 3 equal pieces. Now, if I ordered 8 subs and I'm cutting them into thirds, how many pieces do I have altogether? 8 subs, and they're each cut into thirds. How many pieces? 8 times 3?
24.
24. So that's going to be my denominator. After I get my 8 whole subs and cut them into thirds, I now have 24 pieces to give out. If I eat 2 slices from one of them, how many slices do I have left? I had 24. I started eating before I gave it to the students. How many, Shanita?
22.
22. I've eaten 2 of them. Okay. But wait, that's not one of the answers. Why? What do I have to do with 22 24ths?
We have to break it down.
What's the term? You can say
Simplify.
simplify or reduce. Either one's the same. So they're both even numbers. I know I can always divide by 2 when I have even numbers. And in fact, what that gives me is 22 divided by 2 is 11. 24 divided by 2 is 12. So what fraction of the total is left after I've eaten 2 is 11/12.
Wait, how did you get the numerator?
The 24, Angel?
22.
The 22, because we had 24 to start with, right? 8 times 3 was 24 pieces, but it says I ate 2 of them. So I ate 2.
That makes sense.
So I have 24 total minus 2 that I scarfed down, and that gives me 22. Okay.
Okay.
Okay, good.
Got
Yeah.
it.
Keep asking
So we're
questions.
supposed to divide.
And-
We were supposed to divide with that.
Yeah, and then you
After
have
we got the answer. All right.
right. So 22 left out of 24 to start with. is the same as 11/12. It's the same fraction. All it is it's an equivalent fraction. We've just simplified and reduced it. Okay. Any other questions?
No.
Okay, great.
Can
If
we
you got,
get-
yeah, go ahead.
Oh, can we get more practice with like word problems? Because I don't think my reading comprehension is as good as my math is.
Okay,
So,
sure. Yeah,
yeah.
I can get some for you. Yeah, okay, we can do that. Yeah. Yeah, that's why when you take the tape test, the first part is the math computation where you can't use the calculator, and it's really just computing, calculating. The second part, the applied math, where you can use a calculator, that's the trickier one because it's word problems, and you really have to make sure, that what am I being asked to, what information am I being given, what am I being asked to solve? So, maybe write that down before you attack a question. Okay. This is the last one now. Christina can install a 1/4 meter of Cat5 cable every minute, right? So we have 1/4 meter per minute, and she's going to work for how many minutes?
6.
6. So what am I going to do? What math operation do I want to do here?
The way I did it, how did I do it?
Anybody?
I did it as far as like dividing. I put 6/1, which gave me 6/4.
Okay, good. So
And
you didn't divide, you multiplied, Shanita. Yeah.
yeah, multiply.
Okay, good.
So-
So yeah, so if it's a 1/4 meter for every minute, okay, right? But then we're going to do it for 6 minutes. Notice if I do it this way, then it helps me to figure out, wait, am I multiplying or dividing? Well, I have minutes down here and minutes up here. They cancel out. So I've done it the right way. If I had minutes times minutes, then wait, I probably did something wrong. Or if I had meters times meters, I probably did something wrong. So this helps to set up the fraction this way. So then what we have is 6/4 meters, right? Because we got rid of minutes, and 6/4 is the same as 1.5.
See, now what I did was I divided the 4 into 6, because it will go in 2 times, leaving 1/2. So that was pretty much the
Okay,
wrong
yeah,
way.
but this is the right way. Okay, good. Any questions on this?
Yeah, with the 6. So basically, you was just supposed to simplify the 6/4.
Yeah, you had to multiply.
Then
You got
turn-
6/4 is 3/2, and then that's not one of the answers. So I know I have to change that to a mixed number. So that's 1.5. 3/2 is 1.5.
Okay.
Okay. Questions on this one? So last question. Okay, we're good. Okay. Okay, so everyone but Teresa has it in their email. If you want to look at it again, and Teresa, I'm going to email this to you after class, so you have it too. And again, I'm sorry about getting your name messed up. It'll be good for the next time. Okay. We're going to leave fractions now. I mean, we'll always come back and work with them when we work with ratios, proportions, and percents. We deal with fractions a lot, so we will be coming back to it. But in terms of specific fraction lessons, we're kind of done. Are there any questions about, anything we've done with adding, multiplying, subtracting, and dividing?
Is there an easier way to simplify the word problems that we get, so that we'll be able to understand it a lot better and get the answer right?
Yeah, one of the lessons I'm going to have with you shortly is word problems and how to attack word problems, what keywords to look for. So we will be spending time on that. So yeah,
Okay.
so left, remains, per, all those kind of words that help you decide, wait, am I adding, subtracting, multiplying, or dividing? So yeah, we'll spend time on that.
Okay.
Okay, so what I'd like to do now because we're going to end at 3 today, right? We started at 1. 2 hours is more than enough. What I want to do is work a little with you on binary math. You've done some with Mr. Akins, where you had to add up the different numbers to get to the right amount. So let's take a look at a real world person. This is Diana Tootle. She's the Scottsdale Unified School District Network Engineer. So she's responsible for all of the schools in her district and all of the devices in her district, computers, phones, printers, everything else that's connected to the network, she's responsible for. So let's take a listen to what kind of math she uses in her job, and we'll do some. We'll look at binary a little bit in depth.
Hi, I'm Diana Tootle, a network engineer with Scottsdale Unified School District in Scottsdale, Arizona. A network engineer designs, configures, deploys, manages, and monitors computer network systems. In our
just as an aside, if this is the kind of job you're interested in, she probably has a bachelor's degree, right? So it's more than just your Google IT certification. You might go on to get an associate's 2-year degree in computing science. There's some great programs in the CUNY schools like LaGuardia Community College and City Tech, and a lot of other schools have those 2-year associate's degrees. And then from there, you can transfer into a 4-year bachelor's program. If you get your associates, which takes 2 years, then you probably only need 2 more years to finish and get a bachelor's. Do you need that? No, you don't have to have that. You're going to have plenty of job opportunities just with your Google certification. But one of the things, as you're working with Adria and she's placing you in jobs, one of the things when you're going out for a job interview is to ask, do you support additional education? Do you give me time off if I want to pursue a degree? Do you even pay for the degree? And there are places that'll do that. So if you're interested, that's always something to look into. Are you going to help support me get my associates, get my bachelor's, even get my master's, right? So again, there's plenty of jobs where you don't need that, but for some of you, if you're interested in those jobs with more responsibility, certainly, there's a lot of opportunities if you get higher degrees.
School district, we support 36 different sites with thousands of computers and thousands of users. I ensure the stability of our network, which allows information sharing and internet connectivity for our users. Luckily, our network is stable enough that we don't run into very many problems, because with 36 sites being down at one time, that could be a real problem. I don't think people realize the magnitude of math required in the computer industry. Every device.
And I'll just pause again for a second. So with her responsibility with 36 sites, she probably has a team of IT support techs like you will become, going out to these sites and helping to hook things up, to problem solve, to get printers up and running, new devices being added. So obviously she's not doing all the work herself, but she probably has a team of IT techs working with her for her.
Of a network, printers, servers, workstations, phones, all require an internet protocol, better known as an IP address, and they are unique to every single device, and they establish connections between devices, locations, and resources. An IP address is composed of 4 octets. Octets being octet 8, it's groups of 4 numbers separated by a decimal. Okay, so for instance, an IP address would be 10.11.12.13. That's 4 octets. Computers only recognize ones and zeros, even though we type A, B, C, D, 1, 2, 3, 4, 5. So in order to create the octet that is required to make a connection with a different device, a device located somewhere else, then the binary is represented by powers of 2. Given for example, the IP address 10.11.12.13, that number would equate to 2 to the third power plus 2 to the first power, which equates to 10.
Okay, so let me pause for a minute. So let me just 1 second. Sorry, I'm going to sneeze.
Bless you.
Spring allergy, sorry. Okay, so if the IP address is 10.11.12.13, the computer doesn't see it that way, right? Because the computer is going to translate that IP address into binary code. So how does the computer see the digital, the base 10 number 10? It has to put together powers of 2. So for the computer, 10 is equal to 2 to the third power, which means 2 multiplied by itself 3 times, 2 times 2 times 2. So 2 to the third power is 8. And then 2 to the first power is simply 2. So 8 plus 2, and that gives you 10, right? So that what the computer is going to do is going to see 2 to the third plus 2 to the first, which together makes 10. Any questions on that? Good. Okay, so let me let her continue. Okay, Diana. Okay, so let's take a look at 1 second. I don't think I turned the sound on. But all she said was 2 to the third power plus 2 to the first power plus 2 to the 0 power equates to 11. So let's take a look at that. So again, 2 to the third is 2 times 2 times 2, which is 8. 2 to the first power is simply 2. And anything to the 0 power is 1. Any number raised to the 0 power is defined as 1. So that gives you 8 plus 2 plus 1 is 11. So again, if you have an IP address with an 11 in it as one of the octets, the computer's going to see it as 2 to the third plus 2 to the first plus 2 to the 0th power. Questions on that? Okay, let me let her continue. Remember to share the sound this time. Hear her.
2 to the third power plus 2 to the second power is 12.
So that's 8 plus 4, right? 2 to the third is 2 times 2 times 2 is 8. 2 squared is 2 times 2 is 4.
2 to the third power plus 2 to the second power plus 2 to the 0 power is 13.
Again, so we have 8 plus 4 plus 1 is 13. So what the computer is doing in the background is translating the base 10 numbers, 10, 11, 12, 13, to the binary equivalent.
This will work for any number between 0 and 255.
Okay, so again, I think as you learned with Mr. Akins, there are 256 possible combinations for an octet or a byte, right? So you have 1, 2, 3, 4, 5, 6, 7, 8 positions in a byte. If they're all 0, 0, 0, 0, 0, 0, 0, 0, and 0, that's the lowest possible value, and that's going to be the 0, right? But if they're all turned on, if all of these bytes are turned on, 1, 1, 1, 1, 1, 1, 1, and 1, if all of the switches are on, then what you have is 128 plus 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, and that equals 255. And that's the highest possible value that you have for an octet or a byte. Together, that makes 256 possible combinations, which, don't forget 0 being the lowest, 255 being the highest. Sorry, there
So
was
this is multiples of 8, yeah, because I'm looking at how you put 128 and then went all the way down. So I was asking, like, it just looks like the 4 times table. That's why I'm asking.
Right, it's actually, it's powers of 2. So let's take a look at that for a second. This is 2 to the 0 power, which is 1. This is 2 to the first power, which is 2. This is 2 squared, which is 2 times 2 is 4. This is 2 cubed, 2 times 2 times 2 is 8. This is 2 to the fourth power, 2 times 2 times 2 times 2 is 16. This is 2 to the fifth power, 2 times 2 times 2 times 2 times 2 is 32. 2 to the sixth power, 2 times 2 times 2 times 2 times 2 times 2 is 64. And finally, 2 to the seventh power, 2 times 2 times 2 times 2 times 2 times 2 times 2 is 128, right? So there's powers of 2, right? So again, whether a one of the bits is on or off, if it's off, you don't count it. If it's on, you count it. And we'll spend more time with that to reinforce what you learned with Mr. Akins with bits and bytes.
And Mr. T, where did we get those numbers from? The 1 over, like those fractions.
Okay, so yeah, they weren't really fractions. So what we have is for any octet, right? Octet means 8, or it can be called a byte, B-O-I-T-E. An octet has 8 positions. Oh, what happened? Where'd it go? 1 second. Oh, I put it in black. 1 second. I have to change that to white so you can see it. Okay, now you can see it. There you go. Okay, so what that means is for an octet, there are 8 positions. 1, 2, 3, 4, 5, 6, 7, and 8. We're going to count from right to left. So what that means is the first position is 2 to the 0 power, or in other words, 1. The second position is 2 to the first power, or 2. The third position is 2 squared, or 4. The next position is 2 cubed, or 8. Then 2 to the fourth, or 16. 2 to the fifth, or 32. 2 to the sixth, or 64. And then finally 2 to the seventh, or 128. Now, depending on whether these bits, each of the 8 bits is on or off, you're going to add up all of the ones that are on. So for example, let's say I give you an octet that's 0, 1, 0, 1, 1, 0, 0, 1, right? I want to know what that's the computer's octet or byte. What does that equal if I want to know what that equals in decimal math, base 10, which is what we're used to? Well, I'm not going to count any bytes. Let me make that bigger, and I'm going to cross it out with red. Okay, I'm not going to count any bytes that are turned off. This is 0, that's turned off. 0, that's turned off. 0, that's turned off. 0, that's turned off. So I'm only going to count the bytes that are turned on, and that means what I'm going to do is I'm going to add up 64, 16, 8, and 1. So this makes, let's see, 88, 89. So in decimal math, if I did my math right in my head, that would be the equivalent of 89 in base 10 in the math that we're used to. In the binary math that when the computer uses, it's 0, 1, 0, 1, 1, 0, 0, 1. And that string of 8 bits, that byte or octet, is equal to 89 in decimal math, because I'm only counting the ones that are turned on, which is the all the ones. So that's the 64 plus a 16 plus an 8 plus a 1. I'm not going to count the ones that are turned off. Think of it as a light switch. Remember that the early computers didn't have keyboards, didn't have programming, didn't have monitors. The way those women with the roller skates going up and down were programming the computer was turning switches on or off to program it. Switch turned on, you count the byte. Switch turned off, you don't count the, I'm sorry, you count the bit. Switch turned off, you don't count the bit.
So you just added the ones that were on.
Exactly. All the green ones that are on, the red ones are off. I don't count them. Let me grab that screen because that's a good one, I think.
Okay, got it.
Okay, great. Okay. Any other questions on that?
No, I have to do that part. I didn't get to do that with
Okay.
Mr. Akins.
Yeah, I think that's in the bits and bytes, the first one.
Yeah.
Yeah, okay. It'll become clear once you do that. And we're going to spend more time on doing this too. So this isn't the Only time will see it. Okay, there I am. Okay. Any questions before I erase this and continue?
Like, what does all that
Yeah,
do, Mr. T?
I'm sorry. First, G and then Jose.
What does all of that do, Mr. T?
Okay, so that computers only talk in binary. They only talk in ones and zeros. So if you have, every time you're typing on your keyboard, whether it's a letter or a number, behind the scenes, the computer is converting that to a byte, which is a binary digit. And it's, again, it can vary anywhere from 0 to 255. And that's what the computer understands. When the computer has to send you something, it's going to take its binary and convert it back to decimal math, which is what we're used to, base 10 math. So 0 is 1, 0, 1, 1, 0, 0, 1 is the computer's binary way of showing the value of 89. For us, it's 89. For the computer, it's 0, 1, 0, 1, 1, 0, 0, 1. And they're equivalent. One is base 2 for the computer. One is base 10 for us. Does that help?
Thank you.
Okay, Jose, you had a question? Or no?
Yeah, I was gonna ask something about the bits. There's two different kinds, right?
Yeah, a bit can be either 1 or 0. 1 is turned on, 0 is turned off. Right. So that's the only two values that a bit can have. Computers can only count up to 1, either 0 or 1. But if you string 8 of them together, it can count anywhere up to 255. If you need bigger numbers, then you string.
That's what I was talking about.
Yeah, if you need a bigger number than 255, the computer will just string more than one octet together or more than one byte together. Right.
Okay.
Okay. These are all really good questions. I'm glad you're asking. Any other questions before I let her finish her video? Okay, we're good. I'll erase that. I did capture that and put it in your the email that I'm going to send. Okay, let's let Diana finish doing her thing. Am I still sharing the sound? I am. Okay. Okay.
As I was studying math when I was in school, I knew it would be a part of my everyday life because finances and purchases that we make. I really had no idea that I would use it on a daily basis the way I do in my job as a network engineer. It is actually identifier for almost every piece of equipment I work with almost all day long at work. I recommend that anyone that is interested in computers, a computer field, a technology position, math is going to be very important in your studies.
Okay. Okay, thank you, Diana. I like her very much and the way she describes that. And I think she's a really great role model, right? So, we have to break the myth that tech and IT is just for white guys, right? That's a myth, it's a lie. And there you have a really accomplished African-American woman who is taking care of 36 sites in her school district. So a really good role model for all of you, male or female, no matter what your ethnicity is. I think it's great to have to see that. Okay, so Diana told us that IP addresses are composed of 4 octets, also known as bytes, B-Y-T-E-S. For example, 10.13.11. 10.12. Sorry, I'll throw it again. 10.11.12.13. And the coding behind that is binary, right? Powers of 2. So it's all, 2 to the 0, 2 to the first, 2 squared. So let's watch Computer Basics 3 binary code and see how the code works. What I'd like you to do while you're watching it, let me find it, here it is to think about these. I'll put it in the chat. Think about these questions. What's the definition of binary code? What does a 0 represent? What does a 1 represent? And I keep meaning to change that. What can a string of 8 zeros and 1s represent? Okay, so let's watch this video. This is from Free Code Camp, and I really recommend if you subscribe to any YouTubers, that I really recommend you subscribe to Free Code Camp. And what you do when you subscribe is, if you haven't done it before, You can see here, I've clicked on it that says subscribe. So I've subscribed and I have all. So anytime Free Code Camp releases another video, I get a notification in my email, or actually a notification in my YouTube app that there's a new release by Free Code Camp. And again, I follow a few different tech creators, but I also follow mostly musicians and other things. But this is a good one to follow. This is Brianna. I really like her. She's clear the way she describes things. So let's watch this first video. We're going to watch a few with her.
Hi, this is Brianna from Free Code Camp, and today we're going to talk a little bit about binary code. Now, binary code is a really, really basic, simple computer language where there's just ones and there's zeros. There's two things, ones and zeros. Ones meaning on, zeros meaning off. So think of like a light switch, which in some cases in super old computers there was an actual switch which was either on or off. One being on, zero being off. So bunch of ones and zeros, they can mean pretty much anything, but really they're mostly meant to be numbers and letters. We're going to go in a little bit on how you actually decode binary or translate a number to binary code, but really, as you guessed, you can usually just Google binary translator and have that figured out. The most important part of this is you understand the concept that even basic things like zeros and ones can translate into something really, really complex and is the basis for all of the computer languages and programs that exist today.
Okay, that was a short one. In subsequent videos, we'll go more into, we're going to see Brianna again and we'll go more into detail. But let's see if we can answer these questions. So what's the definition of binary code? Binary code is
code that computer uses to translate whatever, I don't know, whatever the user wants to write, I guess.
Yeah, excellent. Yeah, it's the language that computers use to communicate with us. And again, you know, you're typing in letters and numbers, the computer is translating those to bytes behind the scene. And again, when it's sending information back to you, it's doing the opposite, right? What does a zero represent? Anybody?
You said zero?
Zero.
Zero represents the machine that's off.
Off, right. So think of a light switch. If it's off, that's a zero. And one is the opposite, is on, right? And again, as Brianna mentioned, early computers, they actually were switches. And the way you would program it is to flip all these switches either in the on or off position. Before computer languages were invented, before keyboards, before monitors, that's how you would program these big things like ENIAC and UNIVAC. Okay, and what can a string of 8 zeros and 1s represent? It's any letter, number. Yeah, but if you have a string of 8 of them, it can represent any letter, number, symbol, command. So, you know, if the letter A has a byte behind it, you know, a string of 8 zeros and 1s. The letter T has another different one, 8. A string of 8 zeros and 1s. So depending on which bits are on and off, it's going to range from 0 to 255, and it can be anything from the letter A to the number 1 to the space bar to print to close to the number 57, anything, right? So that's what computers do to communicate. Okay.
And Mr. T,
yeah.
You said 0 represent off?
0 is off. Yeah, think of a light switch, and 1 is on. Yeah.
Thank you.
Yeah, good. And again, if you have that string of 8 zeros and 1s, do you remember what you did with Mr. Akins? You had a number to the left, and then you had to decide, you had to turn on which bits make that number. So if you had a number like 96, you would turn on the 64 and whatever else added up to 96, right? And then you wouldn't turn on the other bits. So by turning on certain bits, that's going to add up to different numbers. Okay.
And Mr. T, you said what was the definition of binary?
It's the language that computers use to communicate, right? So
okay, thank you.
Yeah. It's and again, since the early computers, since UNIVAC and ENIAC and all those computer languages were invented, COBOL was the first one invented by Grace Hopper. Again, another a woman in tech who thought to herself, no, this is not how people communicate. I'm not just going to have zeros and ones and flipping switches. We need a language that people can type in. So she created COBOL, which was a business language where you had commands like print and open and add and subtract. And that was the very first time that people could type in English words and direct the computer to do something. And then since then, we've had, all kinds of languages, Pascal and BASIC, and then A plus, C, all kinds of different computer languages, but all going back to Grace Hopper's initial one. She saw that you had to have a social component to dealing with computers, not just a mechanical component. Okay, so we've done a lot today. We finished our unit on fractions. You had a quiz. We went over that, and now we've dipped our toe in a little bit into binary math to complement what you've learned with Mr. Akins. So I'd like to call it a day. We're ending early again because we started early at 1. Are there anything anyone has questions on about fractions or binary or anything at all before we close for the day? Yeah, G. G and then Shanita.
She said that there are 256 possible something.
Right. So again, let me pull up a whiteboard for a second.
But what was the word? Possible outcomes or
combinations, maybe is
combination. Thank you.
Okay, 1 second. Just try to get the whiteboard. 1 second. And Shanita, you had a question?
Oh no, it's okay.
Okay. Oh, I just got my Zoom just crashed. Let's see what's happening. Dang, it's crashing again. Listen, if the Zoom crashes and closes, we're done. Oh, okay, I came back. Okay, but if all of a sudden everything closes, we're done for the day. Just give me a second. I just want to hopefully try to open the whiteboard again. I don't know what happened. It caused everything to lock up. Why can't I move the whiteboard? Zoom has changed. Okay, I don't know what's going on with Zoom. I'm not going to try to open a whiteboard again. Let me just pull up a blank Word document. 1 second. And I can just write on that. Okay, hold on. Let me just go full screen. Page width. Yeah, okay. Okay, so, really the question is about those combinations and bits and bytes. So let me just do that once more, and then we'll end, just to reiterate, reinforce, revisit what we were talking about. Okay, so when you have a byte or an octet, right, that's going to be 8 positions, right? So what we have is 1, 2, 3, 4, 5, 6, 7, 8. And then the way the computer counts them is that it's by multiples of 2. It's always base 2 or powers of 2. Start with 2 to the 0 power, 2 to the 1st, 2 squared, 2 to the 2 cubed, 2 to the 4th, 2 to the 5th, 2 to the 6th, and 2 to the 7th. Right. So this is equal to 1, 2, 4, 8, 16, 32. Did I just write 13? That's my dyslexia coming in. Okay.
So it's no 3 at any time.
You want to make 3?
I was wondering.
Yeah, so let's see, how would the computer make 3? Well, 3 is 2 plus 1, right? So if I turn this one on, let me make that green just to show that it's on. If I turn this bit on and this bit on, but I'm going to keep all the others off. I'm going to keep those bits off. I'm only going to count these 2 because those are the ones that are turned on, and that's going to give me a 3. So the binary code, Shanita, for 3 is 0, 0, 0, 0, 0, 0, 1, 1, and that's a 3. In decimal, in binary, it's 0, 0, 0, 0, 0, 1, 1, right?
Okay, but that's the number one thing I know I gotta catch up on. I gotta do that whole thing because I didn't get to do that.
Okay, yeah, that'll really help because you have to actually click on the bits to add up. Okay, so give me another number, somebody, and we'll do one more. and then we'll
Mr.
end.
T, I'm still trying to make sense of this, but how it makes sense is like LCD lightings, how they do them.
Yeah,
You know,
I'm not
like
familiar with that. Yeah.
I'm just saying, like, you know, this bulb is on, that bulb is
Oh,
on,
okay. Yeah,
that
yeah.
bulb is on,
Yeah,
and
think
it
of it that way.
says some shit like, "Will you marry me?" or "Happy New Year."
Okay.
You
Yeah.
know,
Right. Yeah.
like
Okay.
that's the
Yeah.
only way I'm trying to understand this whole system.
Yeah. Okay. Good. So let's watch the language, and let's try another number. Gee, give me a number. Any number from 0 to 255.
Well, I
Number.
turned 30 years old this
uh,
year, so that's a number.
I'm sorry. Say it again.
I turned 30 this year, so that's a
30.
number.
Okay. So the question is, if 30 is the decimal number, how do we make 30? So we can't start with 32. That's too big. So we know that these, actually, let me put those in red.
So that's going to be off.
This is good. That's off, off, off. Right. But what we can do is we can turn on 16 and we can add 8 to it, right? 16 and 8 is 24. Is that right? Yeah. And then we can add 4. That makes 28. We can add 2. That makes 30. And we're done. This one will be off. So and let me make that red just so we can see the difference between on and off. So your age in binary is 000111110, and that equals 30. Because what we've done is we've turned on 16, 8, 4, and 2, turned off everything else.
So the only thing that is on is between 2 and 16.
Right, because that adds up to 30. We can't
And
turn
everything
on,
else is off.
yeah, we can't turn on 32, 64, 128. Those are too big, right?
I think that's how LCD lights work.
Oh, okay, good. I didn't know that. So I just learned something new. Great. Okay, somebody, we'll do one more number. Should we do my age? I'm not going to tell you my age.
27.
Oh, yeah,
32.
32.
21.
Well,
That's
32 is too easy because it's just one. Okay, so we want to do 21, which I can't remember being 21, but I know I was 21 once. So we can't use a 32 or a 64 or a 128. Those are too big, right? So what we're going to do is we're going to turn on 16, and 16 and 8 is how much?
16 plus what?
And 8. The next one's 8.
What, 24, right?
That's too much, right? Because we want to do 21. So we're not going to turn on the 8. How about 16 and 4? How much is that? 16 and 4?
20.
Wait, what's the number?
21.
6.
And then
6
0
so-
for 2.
Good. 0 for 2, G says.
And
'cause
then 1 for 1.
Oh, 1 second. That should be red. Sorry. I want to use the color coding. 2 gives us too much, but then we're going to add the 1 here. So what we have is 16 plus 4 is 20 plus 1 is 21. So the age 21 in binary is 000101101, and that adds up to 21. So any number between 0 and 255, you can convert to binary doing it this way. Okay. If the computer needs bigger numbers, it strings more octets together, right? Good. So any questions on any of this before we end? Any more questions about binary and how the computers calculate it?
I thought it was impossible to understand this.
You got it now?
That.
Okay, good. And we're going to return to this, so we'll spend a little more time on this. Okay, everyone. So it's almost 3. I told you we'd end by 3, so you have 8-minute break.
And what time do we have to be in class tomorrow?
9 to 4 every day.
Okay.
We almost never go all the way to 4 sometimes, but almost never. But always 9 a.m. sharp. Be in class. Okay.
Okay.
Okay, great. Any other questions before we end?
No, sir.
Okay, great. It's been a very busy day for you. First with your Google and then with me. So you need a break. So take a break now and take care of yourselves. Right. You need that self-care. Right. And I'll see you all tomorrow.
Okay.
Have a nice day.
All right.
Okay,
Bye-bye.
Bye bye.
Bye.